Hello, welcome to episode 6 of Daryl Show Your Work, where this will be part 2 of our obfuscation of lab. And in this portion of it, we'll be going over asymmetric encryption, also digital signatures, and I'll touch on elliptical curve algorithms as well as one-way hashing of functions. All right, so with no further ado, let's get into asymmetric encryption. So I've already got into our directory of where our files are that we're going to be working with this asymmetric encryption um, lab. So the algorithm that we're going to be using for this is RSA, which is short for Rivas, Shamir, and Adelman, who are the mathematician developers of this particular algorithm. And this is a key pair encryption algorithm, which can be either a 1024, 2048, or 4096 bits long. So that's the level of strength that this encryption algorithm can have, and it is a key pair algorithm, meaning that you'll have both a private and a public key. So what we'll be doing is we'll be creating first a private key, and then we'll be creating a public key derived from that, which can then be used to encrypt and then decrypt files. So let's get started here. So we're going to be using the open SSL command line tool again to do this. So first thing we're going to do, we're going to say open SSL and then gen RSA, telling it we want to generate an RSA private key. So we're going to say dash out and private key. We're going to output that to a .pem file called private key.pem. All right. And then we're going to let's make it 2048 bits long. All right. So I'm going to hit enter. Just looking at my syntax here. We should be good. All right. So it looks like that was successful. So in order to check, let's see what that file looks like, what our private key should look like. And it should be a bunch of several lines of non-human readable language if we did this correctly. But let's see. And indeed, so that's our private key. So you always want to make sure that you have this private key stored somewhere securely, because if an intruder or someone else other than yourself gets a hold of this private key, it kind of just makes the whole thing moot. The whole privacy and everything that you're trying to protect, it just kind of falls apart, because then if attacker has your private key, then they could pretty much decrypt everything that you've encrypted using this. So always best practices, always secure your private key somewhere where you can that you can get to with several layers of security. All right. So the next thing we're going to do is we're going to generate a public key from our private key. So we're going to go back and we're going to do open SSL. We're going to do RSA. This time we're just going to do RSA and not gen RSA. All right. Then we're going to say -n. All right. So we want to tell it that we want to use this private key, the one we just created, this private key, the private key stored within this PEM file, and we want to output. We want it to take that and create a public key and output it to a file called key.pub. And then we're going to tell it that it's going to be a public key output. All right, so just checking my syntax here, making sure I'm good to go. Hit enter. All right, as you can see, openssl telling us it's writing a RSA key for us. All right, so let's take a look at that newly created public key. All right, so we're going to do cat key.pub. That's the public key file we just created. So I'm going to hit enter. And that's our public key. So this is what you know, this is what's okay to share with the world, to share with those who you're communicating with, because this is what they would need they would need your public key in order to communicate with you using this key pair encryption algorithm. All right. So the next thing we are going to do is we're going to use these keys to encrypt and decrypt a file. All right, so we want to check. I'm going to show you what file we're going to use to do that. So I'm going to do a list. All right, so within this directory, you see we have a rsa.txt file. All right, so we're going to what we're going to do is we're going to first encrypt this, and then we're going to decrypt it. All right, so first, let's first read what this file says, just so we make sure that everything works the way it should. So we know what it says before we start encrypting and decrypting. Let's do a cat rsa.txt. All right, so we know that it has our favorite term in there, cryptography. All right, so now we're going to begin to encrypt this. So we're going to go back to openssl, and then we're going to say rsa, then utl for utility, and then dash in rsa dot txt. So we're telling it which file we want to encrypt. And then we're going to tell it we want to output this file to a file called rsa.enc. So it's going to store the ciphertext that it creates for the clear text cryptography. It's going to store that ciphertext in that rsa.enc file for us. All right. So then I'm going to pubin. All right. And then I'm telling it what file my public key is stored in. I'm using my public key here to encrypt this this plain text file, and I'm going to use my private key to turn around and to decrypt it. All right, so just checking my my syntax here. So telling open SSL to use the RSA utility to encrypt this rsa.txt file, output the ciphertext to the rsa.enc file, and we're going to use the algorithm, the public key algorithm that we established in the key.pub file. All right, so I'm gonna hit enter. All right, it did not like something that I did, so let's check that syntax again. Okay, so open SSL. Left the A. Well, hold on. Let me see. Did I leave that out? Nope, that looks good. All right, dash. C N rsa.txt. That's right. Out. Let's see. Open. rsa.txt dash out rsa. Huh. Yeah, that should have seemed like that should have. Oh, well, duh. I left the most important part out, folks. I have to actually tell it to encrypt. All right. So hold on, go back and put my dash here. Gotta make sure my syntax is good. All right. And hit enter. There we go. All right. So then now let's check. Let's go to list. All right. Now we have that. Now we have that new file rsa dot enc. So I'm gonna do the cat rsa dot enc. As you can see, it just gives me a bunch of ciphertext. All right. So now we're going to decrypt it. So instead of having to write this whole thing out, I'm just go back in my history here, and I'm going to adjust my my command line here accordingly. So I'm going to adjust this now to say cn or c. So I'm going to kind of excuse me here. So I'm going to adjust this. I'm going to switch this around. So now we're going to be working with the ENC file, and we're going to output this into an rsa dec file, and that's basically where the decrypted plain text is going to end up. All right, and then now I'm going to be working with. I'm gonna just get rid of all of this. All right. So now I'm going to tell it that, hey, now I want you to use the private key stored in this .pem file, and I want you to decrypt it. Go back and add that dash. All right. All right. So we're telling openssl to use the rsa utility. All right, to take the ciphertext that's in rsa.enc and output it to rsa.dec, and using our private key that's stored in the .pem file, and we're going to use that to decrypt it. So I'm going to hit enter. All right, that looks like that worked. So let's check our work. We're going to go to cat rsa.dec. So if this works, it should say the same thing that the original rsa.txt file said, and that is cryptography. So we were able to successfully encrypt a text file, and then with our public key that we created using using openssl and the RSA utility, and then we were able to also decrypt that file with our private key that we created with the openssl command line tool. All right, so that covers asymmetric encryption. So next we're going to move on to digital signatures. And this is usually used when it comes to communication. Like think of like email or something where you want to verify that the contents of the communication are legitimate. So this would be added on as a benefit. A benefit of adding this on to your communication protocol would be it adds a layer of authentication. something called non-repudiation, meaning that the sender cannot refute that it came from, at least from their end, because they have a specific digital signature tied to them, tied to whatever their digital identity is. It's tied to that specific digital identity and only that digital identity. And then it also protects the integrity of the communication that's being said, because it uses, in most cases, it uses a hashing algorithm. And if the value of that encryption looks different than what the regular digital signature usually is, then that's an indication that that message or that something with the sender has been tampered with. But I'm going to show you how this works. So I'm going to use openssl to create a digital signature and show you exactly what that looks like. And I'm going to be creating one. And I'm going to be creating one in order to create a digital signature, you have to create a digital certificate. So I'm going to be creating a digital certificate based on the X.509 standard, and it's going to be with a 4096 bit RSA encryption key. All right. And it's going to be good. And I'm going to set it to be good for 365 days, basically a year. All right. So in order to do this, I'm going to do openssl and then req and then dash x509. So telling it the standard that I want to set it for. Then I'm going to do dash new key and letting it know I'm going to use the RSA algorithm and the 4096 a bit version of it. And then I'm going to do key out to output that to a file, a PIM file called key.pub. Just keeping it real simple. And then I'm going to then also output the certificate that we're creating to a file called cert.pim. All right, and then I'm going to tell it, I'm going to do dash days. And remember, I said I want to do a year, so I'm going to do 365. So meaning this digital certificate associated with this digital signature is going to be good for 65 days, 365 days, and then it's going to expire, and then a new certificate would have to be created and associated with this key. All right, so I'm gonna hit enter. All right, so then I'm gonna enter in my password. I have to enter that in again. All right, so when you create a certificate, it's going to ask you to enter in some information to specifically identify yourself, any sort of demographical information you want to add in. Again, just adding more to that user identity to help with the non-repudiation. So I'm not gonna really take the time and add any of that in, but I'm gonna just scroll through here and just show you some of the information they ask for. So they want you to enter in a country name, your state or province, depending on where you live, locality name such as a city, your organization name, like your company, what unit you work in. So let's say you were in a cybersecurity unit, you would put like cybersecurity. Common name, or like if it's associated with a server, you would put the server name in there, or if you just wanted to be associated with a person, you would put the employee or the person's name in there, and then the email address associated with the certificate. All right, and that's pretty much it as far as digital signatures, how a digital signature is created, and just generally how that whole process works. The next thing I want to get into is elliptical curve cryptography. Basically this is a key pair algorithm as well, just like an asymmetric algorithm, just like RSA, except it makes shorter key lengths. It makes it faster, faster key and signature generations. Those are some advantages of it. Also, the ciphertext is also a bit smaller, and this tends to be used in mobile devices. Now, some disadvantages of it is vulnerable to two specific types of attacks, which is a side channel attack and a twist security attack. And the big problem with the twist security attack is that it could expose your private key. And remember what I said about your private key is that you do not want that exposed, because then the whole public key PKI infrastructure system, it just completely falls apart if the private key is exposed, or if an attacker has that private key. Then they could just pretty much decrypt whatever the user has encrypted with their public key. Okay, so to get started on elliptical curve cryptography, what we're going to do is we're going to view a list of different type of algorithms we can use. And to do this, I'm going to be using openssl again. I'm going to say EC param, and then tell openssl to basically list give me a list of a bunch of ECC algorithms that we can use to encrypt a file. So as you can see, it's a fairly long list here. So I am going to use the SECP 256K1 ECC algorithm, and I am going to output the private key that we get from that. I'm going to output that to a PIM file. So, and I'm using that because it's a pretty strong algorithm to use, especially for a file at rest, 256 bits. So let's get started with that. So openssl EC param. All right, then I'm gonna tell it I'm gonna give it the name of the algorithm, which is prime 256 v1. And then, all right, then I want you to gen key. I want you to generate key for me. Dash no out. Then I want you to output the new private key that you create for me to a file called private underscore ECC dot PIM. All right, so let's check our syntax here. All right, so I'm telling openssl basically to use the from the list of ECC algorithms, to use specifically the SECP 256K1 algorithm, and the way that it does that is and the way that's defined here in openssl is prime 256 v1, and I want you to generate a key and save that key to the private underscore ECC.pim file. All right, so I'm gonna hit enter. All right, didn't get an error, so it appears that that worked. So let's view that new PIM file that we created to see what a elliptical curve private key looks like. Oops, go back here. So as you can see, if you're comparing this to when we were looking at our private key, just using a regular RSA algorithm, the key length is much shorter, and that's even with a 256-bit encryption algorithm. It's a lot smaller, and again, that's one of the advantages of ECC, because the output, the ciphertext output, is a lot smaller, and that's why it's tended to be used with mobile devices. All right. So next thing we're going to do is that we're going to create a public key from our private key. All right. So then, in order to do this, it's similar to the steps that we were taking with RSA, except we're doing this now with elliptical curve. So open SSL, then we're going to say EC. And then we're going to tell it -n, and we're telling it to basically create a public key from our private key that's located in private underscore cc dot pim. All right, now we're going to do, hold on, add my dot. There we go. We're going to do a pub out. We're saying we want you to output this public key to a file we're going to name public underscore ECC dot pim. So both, in this case, both files are going to be PIM files instead of how with the RSA it was like a key.pub. So this time with elliptical curve, we're using two PIM files in this specific instance. All right, so just checking my syntax here. We're saying, hey, open SSL. We want you to from this private key within the private underscore ECC PIM file, we want you to create a public key and output that public key into the public underscore ECC.pim file. All right, so I'm gonna hit enter. All right, so we know that it's working because it says it read the elliptical curve key and it's writing the elliptical curve key. So we want to see what our new public key looks like. We're going to do cat public underscore ECC dot pim, and that's our new public key. All right, so let's see. Let's try to with this. Let's try to create a security certificate with our new private key and store it in a different PIM file. So we could do all the same things with elliptical curve that we did with RSA, and that's including certificate creation. So in order to start creating our security, to start trying to create our security certificate to associate with a digital signature using elliptical curve, we're going to do an open SSL REQ, and we're going to say we want this to be new, and we're going to still use that the X.509 standard. All right, then we're going to say dash, excuse my here. And we're going to tell it which key to use, this, and we're going to use the private key stored in private underscore ECC .pim. All right, and then we want to output that that new certificate. We want to output that to a file called cert underscore ECC .pim. All right, and remember, next thing we have to do is that we have to tell it when do we want the certificate to expire. So I'm gonna tell it the same thing we told it when using the RSA algorithm, and I'm gonna say I want it to expire a year from now. All right, so I'm gonna hit enter. All right, so it does the same thing here. When it starts to create our certificate, it just asks us those same questions. So country name, state, province, a city, locality name, city, company name, what unit do you work in? Do you want to use your name, or do you want to use a server name? What email address do you want to associate with this certificate? All right, and that is elliptical curve. All right, and then we can tell you what we're going to also, let's see what a an elliptical curve created security certificate looks like. So as you can see, I don't think I showed what an RSA one looked like, but an RSA security certificate looks much larger than this. So this is fairly smaller than what we were finding if we were using an RSA. If we created an RSA certificate and we wanted to view, what the ciphertext of that looked like. Okay, so all right, the last bit that we're going to go over, which is fairly a bit more fairly straightforward, is hashing, which is one-way encryption. And this is typically done when let's say you want to, if you're taking some files and you want to encrypt it, but you want to make sure that the contents of that file hasn't been tampered with. So when using a hash function, it gives that particular file a specific value that no other file should be able to have. And so if you were to compare, if let's say I were to take a hash of something today and put it somewhere, and then next week, if I wanted to make sure that nothing in that file changed, then I would check the hash value of that file, and it should give me the same thing it gave you last week. Now, if even one bit of that changes, let's say somebody goes into the file and adds just something as simple as a period, well, then the entire value of that is going to look different, and then that way it's going to tell me and everyone else that, hey, this file has been tampered with, because the hash value isn't what is set to what we initially set it to. So this is good when it comes to forensics and when it comes to measuring the integrity of a file that's perhaps going to be used in some sort of investigation or trial, and making sure that hey, that what the evidence that we originally had has not been tampered with, and that what we are presenting in court is indeed is indeed the information that we originally captured. So again, it all falls under the category of data integrity. All right, so I am going to change directories here to our hashing directory. All right. All right, so the first thing I want to do is we're going to be working with two files. We're going to be working with a file called hash1.txt and hash2.txt, and both have clear text um, language in them. And we're gonna use a SHA-256 encryption algorithm to be able to hash them and make some comparisons and just see those what those ciphertexts looks like when you hash something. All right. So in order to hash this file, so let's say these files, let's say hash 1.txt and hash 2.txt 2.txt. Let's say they are prime evidence, smoking gun evidence that we found somebody committing fraud, and we want to preserve this evidence for court and make sure that it makes it to court and nothing is changed, and we're good to go on that. All right. So in order to give it a hash value, we're going to go to openssl. All right, but then we're going to put dgst for digest. All right, then we're going to tell it, hey, we want you to use sha256 hash 1.txt, and we're telling it to use this specific digest against this file. We want you to encrypt this file with a SHA-256 algorithm, which is a pretty strong algorithm. All right, we're going to do greater than, and then we're saying by doing greater than, we want you to pipe to a file called the output to a file called hash 1 dot dash 256 dot txt. All right, and so what this is going to do, again, it's going to encrypt this clear text well, you know what, before I do that, well, okay, I could show you after this, but it's gonna encrypt this clear text file, and it's going to basically save it to another file that's been encrypted using this SSH 256 hashing one-way hash algorithm. So I'm gonna hit enter. And the thing I want to show you, I want to do a cat. I should have did this before, and just to go through what was in hash.txt. And our imaginations is going to be, fraudulent numbers or the smoking gun needed in evidence. But for example purposes here, so it just simply says hash in it. All right. So let's see what it says now in the file that when we've taken this clear text hash, and then we've did an encryption. We've done an SSA 256 digest encryption on it. Let's see what it says within the file that we just created. 256.txt. That's what the word hash looks like using a SHA-256 algorithm when it's hashed. And remember, this is one way, so this cannot be decrypted. So there is no symmetric key, asymmetric key, no key that's meant to decrypt this. Now there is a way that a hashing algorithm can be decrypted, but it's not something that's done intentionally. So in weaker encryption algorithms such as like MD5 or earlier versions of a SHA encryption, there's a thing called collisions, where basically someone can run a program and basically run a program that runs fast enough to guess matching numbers, and if they do that enough times, there's something called a collision where where that program will match the values of that hash and then be able to expose what the clear text is. And so MD5 earlier hashing digest known as MD5 has known to have collisions, and earlier versions of SHA has known to have collisions. So that's why a lot of those are considered legacies and not commonly used or advised to not use, because they have known collisions as far as clear text values. All right, so the next thing we're going to do is we're going to run the same command, but this time we're going to do it with the hash2 file. All right, and let's, you know what? And before, let's see what hash2 said. All right, so hash2 has lowercase hash and just all lowercase. All right, so we're gonna go back to our command here. All right, then we're gonna do hash2.txt, and then we're gonna give it the same naming. We're gonna give it the same naming convention. All right, so making sure everything is right there. So we tell openssl to use the SHA-256 hash digest against hash2.txt, and to pipe the output of that to hash2-256.txt. So we know that that is the contents of the file that have been hashed. We're gonna hit enter. All right, and let's see what this looks like. So remember, the only thing we changed as far as what was in the file is we changed hash having a capital H and now hash having a lowercase h. And let's see if any one of those, the outputs, the cipher, if the ciphertext output looks anything close to each other. So we're going to do cat. Let me see. Yeah. All right, we're just going to change the one value here. All right, and so we're going to see what this content looks like in here. So as you can see, the only thing we changed was we went from a capital H to a lowercase h, but it gave us two completely different sets of values. And so that's the example that I gave before, how you could change something just very small, even in this case, something just as simple as whether it's lowercase or uppercase of a letter, and the value will completely change. And so that is definitely one of the benefits of a hash function, how a hash function is used in the real world, and how it helps protect the integrity or indicates the integrity of a file. So that would do it as far as our labs for obfuscation. So as usual, please like,